So there's a bit of overlap between today's recorded lesson and what we touched upon at the end of yesterday's, that being on the 3rd of Feb. We're still looking at nucleophilic substitution, but this is the last thing that there is to say about it really. And it's to do with that reaction between a haloalkane and ammonia. And moreover here in this lesson, the fact that the products of this reaction can then go on to react again and again and again up to a point. So there's going to be a few occasions on this video where, to get the most out of it, what you'll need to do when I prompt you is to pause it, spend some time drawing your mechanism, and then unpause and carry on. And along the way, hopefully it will get really repetitive. That might sound like it's boring, and to a point it is. However, that's because you're getting really familiar with it and you've heard it so many times that now it's a case of like, yeah, okay, you've told me that. So, but that's a good way to have it really here. Mechanisms are really formulaic. So there's the overall reaction equation for the combination of that haloalkane with ammonia to make this amine and that product. So the first thing I want you to do is draw a mechanism for this reaction. And once you've done, name the organic products and also this inorganic product. There's no carbon in that. It's a salt, so it's inorganic. Okay, so name all the chemicals after you've done your mechanism. There's your first occasion to pause. Come back as soon as you're ready to see the answer. So here we go. Now I'm going to have to make sure that I've expanded out that CBr bond so that I can have arrows going around it, which is why I've just done the whole thing in display formula style here. Along comes our first ammonia. This one is the one that we labelled as acting as a nucleophile, lone pair donor, electron pair donor. So bond forms with the carbon, bond between C and the halogen breaks. There we go. Giving us not quite the final product here. If it was cyanide or a hydroxide, then that would be everything. This NH3 unit is still present as NH3. In other words, that end's got 4 bonds now because it's just formed a new bond, a coordinate bond to the carbon through its lone pair, and we've got a methyl ammonium intermediate there. Like we said, this is an intermediate. It's not the final product. It wasn't there as a reactant a moment ago. It's an in-between, which hence is why we call it intermediate. Now, the bare minimum to show here is any one of those 3 NH bonds breaking, which means an arrow coming from the bond, and those 2 electrons, this movement of a pair of electrons, they end up in the outer shell of the N, which is why the arrows go in there. Now notice at this time I didn't show something coming along and picking it up. If we're going to think about exam for a while, it's tick, tick, tick for those 3 arrows. Something must come along, if I put it in brackets like I did at the end of last lesson, and take that H. It doesn't just spontaneously drop off. And it's most likely in this case to be another ammonia molecule, which comes along and takes that H by forming a bond with it. That's something that you don't have to show, but if we just left it without that, it would suggest that the NH bond just randomly breaks, nothing causes it. This NH3 collides with it and takes it, okay, but we can omit that. Either way, we get our product, which is CH3NH2. NH3 turned into NH3CH3 plus, and then that has now lost a H. That hydrogen's effectively been lost as a H plus because the NH3 here gained that H, but it didn't gain the H's 1 electron because both electrons in the bond went that way. So effectively that H was a H plus, so NH3 becomes NH4 plus. And we've also got that bromide knocking around from earlier. Again, we tend to just ignore them after we've discarded them, but it's also present. So for exams, for future reference, tick, tick, tick for the 3 arrows. And this structure here has to be correct with that arrow on it. There's actually never any, well, it's very rarely any marks for the products, but I want us to draw them here to keep track of what chemicals are where. Right, so there's the first product. I said that you were going to name them as well. This haloalkane is bromomethane. We know that NH3 is ammonia. This product here is, we're going to call it methyl amine. That's the organic product, the carbon covalent bonded product. And then we've got this pair of ions here, which together are a complete chemical, positive and negative ions, and that is ammonium bromide. Fine, okay. Now, we said it before, but in case you're really keen, that intermediate there we could also name. Ammonium is NH4 plus. We'd call this intermediate methyl ammonium, which is actually pretty logical when you look at it and you think about what ammonium is. Now, the second task for you then is to consider what would happen next. So imagine this: we used a large excess of bromomethane. So some bromomethane has just been used up by that reaction and turned into those products. However, there's still more knocking around because we used an excess of it. So these methylamine molecules that have just been produced by the reaction are also able to act as nucleophiles. There's a lone pair on an N. That makes it a good base. It makes it a good nucleophile. It makes it a good electron pair donor. They're all pretty well the same thing when I say those three terms. So we'll write our methylamine like that. And I want you, once again now, to do the mechanism of those two reacting. And we're actually going to do this 3 times, this time and twice more. So grit your teeth, okay? Again, pause the video for as much time as you need. Same as before, I want you to draw the mechanism, identify the products, and name the organic products. That's all we need this time, just the organic product being produced. So pause and go, and then come back to me as soon as you're ready to check it. Here we go. So yeah, that lone pair on the nucleophile forms a bond with the carbon Br, carbon, breaking that bond. I'm going to try and resist the temptation to keep saying as always, because yeah, we've heard that now, but you can see how these things play out. That is going to give us this structure where you've still got your basically methyl amine there, but now with the lone pair N being a bonding pair to another methyl group, the one that was carrying that Br. Br's gone. I don't need to show it, but I will just to be complete. N has got 4 bonds and therefore must have a plus. Never forget those charges. Like before, a base comes along, something that can take this H away and causes one of those 2 NH bonds to break. Pick whichever one you prefer the look of. I'm going to break that one in the middle. You don't have to show what it was, as I said earlier. Now, what would that be? It might be another ammonia, if there's any NH3 left unreacted. It could be another methylamine, which is going to pick up that and become CH3NH3+. That's an option, methyl ammonium. Or it could be all sorts. So basically, we're just going to say something comes along. There's plenty of chemicals in this reaction mixture which would be able to do that and pick off that H. That takes us to our product. So this is the sort of thing that we saw in the lesson prior to this one. Now we've got CH3NH2 having turned into CH3NH with another CH3 attached where a H was. So the substitution is basically on the carbon, and it's the NH3 group, or the N group, kicking out a Br. But what we've got here is that then actually that N, because it can form multiple bonds, is actually picking up more alkyl groups. So now when we look at it, it's almost like the substitution is a H for a CH3 on the N. But really what's going on is it's the NHX group, like N with however many H's and R's, R being CH3 or something, swatching out BRs. So you can see it gets a little bit complicated. Name of that product is going to be dimethylamine. That's all one word really, but I've written it across a bit because I want to save a bit of space. And don't forget, something did take that H off. Now this time, but this is, I'm going to make a sort of a mistake in order to make a point about it. We could write H plus there. Again, we don't normally show it, so don't worry, because it appears that this H has dropped off and the electron it invested in that NH bond has gone. And so it's H plus, it's lost an electron. We don't get H plus floating around in solution though. That was a base, B. All right, so maybe if I just go back, this is not something you need to add into your notes. Base B, there isn't, well, there is, okay, I don't mean boron, there is the element symbol B, I don't mean that here. Base B picks up that H, and you end up with HB. For example, NH3, HB plus even. I think we're overcomplicating a bit there, but the idea that an ammonia or something picks up that H plus and becomes its formula with an extra H in that, so we'll leave it like that. Keep going. So now we've got dimethylamine. N must always have 3 bonds and a lone pair in this condition, and it can still act as a nucleophile. We'll get to a point when it can't anymore, and that's the next step after this one. All right. So it's still a nucleophile because it's still an electron pair donor. So imagine this, we really did have a lot, whoops, sorry, I made a mistake there. Imagine we really did have a lot of bromomethane floating around. We really used a large excess of it. And a mole of it got used up for every mole of ammonia that reacted here, and then there were more ammonias reacting. Product went in, and there was still bromomethane available, so it went on to another reaction. And imagine this: there's still bromomethane available in the system, in the reaction container, so it can react even more. So yet again, pause, complete it, and then name the product. Keep going through this cycle that we're working our way through. Well, yeah, the lone pair on that N forms a bond with the carbon, breaking the CBr bond, and here we are. We get that intermediate again. Now, this is the last time when there's going to be a H available to drop off, you'll see. So that N had a methyl group, and a H. So if I draw it in a really consistent way, then you can keep track of that. The lone pair on the nucleophile becomes a bonding pair. Maybe I'll use an orange pen for that one this time because the structure's getting quite big. And this carbon here, if I use a different colour pen just to keep track, is a CH3 group, the Br having left to make space for the N. It's got 4 bonds, so you know what you need to do with the charge. And yeah, there's still an NH here, so that NH bond can still break like it did the previous couple of times to give us the product, but this is where that ends now. So a base comes along, picks off that H, bond breaks, so the arrow from the bond to the N, that's the NH bond to the N, giving us our product, which in skeletal formula style would be that. However, we're not working in skeletal for our mechanisms, so we'll just make it clear that those are CH3 groups at the end of those bonds. There we are. I bet you know the name of that. If that was dimethylamine, this one must be trimethylamine. And it's not clear from the structure I've drawn there, but there is still a lone pair on that. N with 3 bonds always has a lone pair, but also the logic behind that is, well, look, this NH bond broke. Both electrons in that bond went to the outer shell of the N. So there they are. Those are those 2 electrons. They were an NH bond. Now it's an N lone pair. H has gone because a base carried it away. We won't show where that went. But it can still act as a nucleophile. So we can still have a substitution reaction happen. So the 4th and final step now is to take our trimethylamine and for the final time show it reacting with bromomethane, another molecule of bromomethane, to see what ends up. And this is where the story will end and gives us a chance to talk about another functional group. So let's get this done. You know that you're going to pause the video, have a go for yourself. And this time I want you to really think, an educated guess is all that I can ask for, really. And unfortunately, I can't read mine, so I won't know what you thought. But what would the name of this product be? What would the organic product's name be? We had methylamine, dimethylamine, trimethylamine. What comes next in the series, do you reckon? So complete the mechanism, think about the name, and then let's find out. For the last time now, that nucleophilic substitution mechanism that we've talked our way through multiple times gives the intermediate N, CH3, CH3, CH3. That's what came in with the N as trimethylamine. Again, just for the sake of clarity, I'll use a different colour. This methyl group is now also attached. It's got a plus. Br has left. Now this time I am actually going to show the Br minus because we're going to need it for the name. Hint, hint. Now I just called it an intermediate because that's what we've been calling it all the way through. But as we noted, there's no NH here. So that second step, or third arrow I suppose, where the NH bond breaks, returns the lone pair to the N. That can't happen anymore because there isn't an NH bond to break. What will not happen is a base coming along and like picking off one of those H's on the CH3. Not going to happen. All right, we're not going to think about why, but really won't happen. So what's this then? So rather than the intermediate, this time this is actually the final product because there's no further step. What do you reckon that's called? I'd love to know. I'll try and use my psychic abilities. I wonder if anyone's calling it tetramethylamine, tetra being 4, methylamine. Not quite. Actually, the name of this particle, the NC4H12, or the N with 4 methyl group particle, it is tetramethyl, but it's no longer an amine. It's a positive ion, N with 4 bonds, so we call it ammonium, don't we? So this species is tetramethyl ammonium. The thing is, it's ionic, or rather it's a positive ion, which means the chemical that it's a part of must be a negative ion. You wouldn't be able to buy a bottle of tetramethyl ammonium without there being a counter ion to match. Since this was a bromoalkane, then there are bromide ions floating around. It could have been iodo or chloro instead, but it isn't. And so actually the complete chemical for an ionic, you must always consider a balancing of charges and therefore the negative and the positive ions being present. The name of this complete chemical is tetramethyl ammonium bromide. Remember that it's a negative ion, so it's bromide, not bromine. So there's a bit more to say about that structure. It's interesting. It's not an amine. It doesn't have the lone pair on the end, which is part of what defines an amine as such, along with the fact that it's got single bonds to the carbons around it, at least 1 carbon, but up to 3. We call that type of chemical a quaternary. Now, we haven't talked about secondary or tertiary yet, but we will. A quaternary ammonium salt. Okay, and more specifically, so this one's a quaternary ammonium bromide. Quaternary suggests the number 4. We might write it as a 4 degree, but never call it a 4th order or a 4th degree ammonium salt. Call it a quaternary ammonium salt. But it's one where the N has got 4 carbons bonded to it. Now, I'm not going to make you go and do another series of mechanisms like this because they're all pretty well the same, aren't they? So I'm not going to say now go and do the whole thing again for ethyl iodide because iodoethyl. I don't think that helps. But a couple more things to say. First of all, the overall equation. Let's see if we can work this out. Now, we have got a problem here with, we don't know necessarily what the base was that was picking off the H, but I'll help you think your way through that. We're not really too interested in it, to be honest. Now, what's happened? Well, we took our CH3Br and we reacted it with ammonia. We turned it into CH3 4N plus, you can see how that is, that structure there, tetramethyl ammonium written, and there is the negative ion bromide as well. Because those charges match, I could have actually just not written the plus and the minus, I could have just written it as NBr, but the worry I'd have there is that people are going to think there's like a covalent bond between the N and the Br. There isn't, it's an ionic attraction. The obvious difficulty comes with, well, what about the side products? Let's work backwards and let's see what we can piece together. I would just say that this overall equation here is a bit of extra and a bit of challenge, but let's see if we can use a bit of logic to put together quite a complicated balanced equation from our knowledge of the mechanism. 4 methyl groups were added, and we appreciate that each methyl group originated from a bromoalkane. So we must have had 4 CH3Brs. Every substitution, well, we had 1 ammonia at the beginning, right? If we just try and keep tabs on this, at the beginning we had 1 ammonia doing that reaction, and then it was that same N that went all the way through as NCH3 with 2 H's, with 3 H's, and so on, right? So it was that same N. So we had like 1 original ammonia, which is the N that leads in there. Now, if that was everything, then we'd say, okay, 4 BRs went in, and so like 3 BR minuses came out as something other than the last one, which ended up with the N plus. I think I'm going to regret going through this, to be honest, now I've got stuck into it. How did that work? Well, all 3 of those hydrogens in the ammonia were kicked out, right? So there were like 3 effectively H pluses as well. So we've got this reacting ratio of 1 N, H3, ends up as that N there with different atoms on it other than H's. So one of those to one of those, that's the one that acted as the nucleophile. That's the one that started reacting and gathering atoms. Those 4 methyl groups are there, that's fine. 4 BRs, one of them ends up kind of as part of the ionic, there were 3 others. All 3 H's left, as we saw in the mechanism, effectively as H+. Now, I just want to make a comment as well. This is really where I wanted to go with this. What we must not do is ever suggest that there were like 3 hydrogen bromides present. No, there weren't. There was bromide and there was a different base, something that came along and picked up the H. So whatever that base was, let's imagine for argument's sake, it was another 3 ammonia molecules. And so those there would be 3 NH4 pluses that came off. And I think that's good enough. So we'll pretend that there were 3 more ammonias. So overall, we had 4 of the haloalkane reacting with the same number of ammonia molecules, one of which was the N in the organic product. The others carried out a hydrogen each to give our organic product, which we ended up here with a quaternary ammonium salt. One of the bromides is there. The other 4 Br atoms were left over, and they went with the other 3 ammoniums. But that's just one possibility. The only variation on this would be like what the other 3 particles there were. Were they NH3s or were they methylamines? And did you get like methyl ammonium bromide and so and so and so and so? But anyway, we can piece something together from appreciating what the fate of these atoms was, where they ended up, and the mechanism gives us that. Now, we'll save classifying amines for another day, because otherwise this video is going to be getting a bit long. No, we better do it now. Sorry about that. So, classifying amines. We're going to be messing around with amines a little bit in some other mechanisms as well. So all there is to say here is if we're calling that one a quaternary, what are the ones before it called, which are actually amines? So if you've got a carbon, if you've got a nitrogen that's only got 1 carbon on it, now I'm purposefully going to leave that carbon blank. It could be CH3, it could be like a propyl group or a branched hexyl group, it could be anything. But the idea being that you've got 1 C bonded to the N, then we call that a primary amine. Okay, primary amine. You can call it a 1 degree amine, but when I say 1 degree, I never mean I want you to call it a 1 degree or a first order. I'm just writing it, that's what it looks like. That's our shorthand for primary. Call it primary, don't call it first order or anything else. You'll never guess how this pattern plays out then. If you've got an N such as dimethylamine that we had earlier, that has 2 carbons attached, then it must also have a hydrogen. Again, those carbons would have 4 bonds as always. Then what do you suppose we call it? Well, yeah, hopefully you're thinking it. We call it a secondary amine. And that's our shorthand for it, but please call it secondary whenever you need to. Third order amine is much better, called a tertiary amine. So that's got 3 carbons on the N, tertiary. And this is it basically, this is what we're saying, it's just categorizing them. And a tertiary amine can undergo 1 more substitution with a haloalkane. That took us to our quaternary ammonium salt. So at that point, it's got 4 carbons bonded to it. It must have a charge. Because of that, it's actually N+. It's not an amine per se, it's an ammonium salt. And as we've already said, that'll be a quaternary ammonium. Now I'm going to say salts, but must stress that the salt should be specified. Here I'm just going to say X-, fluoride, chloride, iodide, bromide, whichever. So a quaternary ammonium chloride or bromide salt. You get the idea, hopefully. Right, good. The truly final thing to put onto this now then is just an observation of, well, what if we wanted to make, I don't know, what if for some reason, because of its chemical properties, what we really wanted was trimethylamine, and what we didn't want was quaternary tetramethyl ammonium because it's less useful, for example. We really don't want much dimethylamine, we want this one. Or, to make it even more complicated, possibly, maybe we want this one and we don't want the ones either side of it. There's not much you can do about that, to be honest, because there's a lot of randomness in this. So remember that all reactions happen by collisions, and we can't control what collides with what. In fact, we should assume that everything collides with everything. That's probably a sensible assumption. But what you can do is like sort of limit the amount of further substitution that's possible. So to finish off, we'll just talk about tweaking the conditions. If you've got a haloalkane, I'm not going to do any more mechanisms now, plus ammonia. then potentially through secondary amine, tertiary amine. Now I'm doing this as single-headed arrows. It's definitely not reversible, so I'm going to have to take that back. Amine, and then because I've run out of space, I'll put it down the side there. Quaternary ammonium salt. The way that you'd get more quaternary, so if you wanted more substitution, so as we go down that trail there, we're following this sort of path of further substitutions, then the way to achieve further substitutions is to make sure you've got plenty of haloalkane. So if you've got excess haloalkane, then you're going to achieve more substitution, because once that secondary amine has been formed, it can react again and again. So excess haloalkane will lead to more substitution, and that's going to push you towards quaternary if you've got enough to get all the way there. So how would we limit substitution? If we wanted to, if I just say that's going to react with Rx, I'll need to explain what Rx is, obviously. Rx would be our shorthand for haloalkane. Yeah, it's very shorthand. So Rx, R suggests some kind of alkyl group, for example, CH3. So we quite often use R as a placeholder for hydrogen or alkyl. X is commonly used shorthand for a halo atom. So Rx would be like CH3, Br, or propyl with an iodine on the end, and so on. Anyway, more of that, more of that, more of that. If there's enough haloalkane present, then it will go all the way to full substitution. How would you actually limit the substitution? Well, I suppose you could say we just don't use as much haloalkane. Okay, yeah. What you're saying there really is use an excess of the other reagent. So one of these two has to be the limiting reagent. What you could try and do is try and put them in perfectly matched quantities. I'll make a comment on that to finish. But if you use excess ammonia, or to be honest with you, outside of our course, if you were going to start with secondary amine and you only wanted to go to tertiary, you use an excess of the N-containing group. So if there's an excess ammonia stroke amine, depending on what you're starting with, then that's going to limit the amount of substitution possible. And so you won't get as far as, like getting all the way up to a quaternary. So I'm saying, look, it will stop before it gets there. Now, final thought. I could work out the correct number of moles. If I've got 1 mole of ammonia, and what I really want is a tertiary amine, I can work out the reacting ratio of like how many how many haloalkane molecules I need per ammonia. I could look at a balanced equation and work out the reacting ratio. Thing is, I can't control what collides with what, as we said earlier. So if I work out just the right number of moles of haloalkane to put with 1 mole of ammonia to get a tertiary amine, then the problem I'll have is that I'll get some tertiary amines, great, but I will also get some quaternaries, because some of those tertiaries will collide and react and produce a quaternary. And that'll mean there aren't quite enough haloalkane molecules for all of the secondaries to turn up to quaternaries. So you always get a mixture of products. So I'm writing in orange now for some reason. You always get a mixture of products. You can't control where the substitution stops, because some will collide, and before you know it, they're quaternary. And others will take a bit longer before they find the right thing to collide with. And by the time they do, they'll turn into that, and there won't be enough Rx left, haloalkane, for it to turn again. So you always get a distribution of products. The more haloalkane, you'll get more substituted products. Less haloalkane, i.e. more ammonia or amine, you'll get less substitution. But you can't control. You can't only get that. You're bound to get some either side of it, just because of the random nature of the collisions. So my reaction mixture at the end might contain, depending on how much of everything I used, if I used a large excess of haloalkane, there might be some of that left over. It will contain all the substitutions. It will contain CH3NH2. It will contain CH3, 2 of them on an NH. That's a secondary. That's a dimethyl. It will contain NCH3, 3, or if you prefer, CH33N. It's the same thing. And depending on how unlucky you got, if you didn't want it, though they are actually quite useful, those quaternaries, you might have even got something like that. Now, you can rewrite that. I've actually written that. I don't like the way that's looking. I'm going to rewrite it, just switching something around. It makes no difference, but there you go. So you could have a mixture of all of those. How would you separate the one that you want from all of those? Well, the way I'd do it is by distillation. I'd assume that these are all liquids at room temperature. An exam question might tell you that they are, or give you the melting points and confirm it. Distillation could be used to separate all of those. Now notice that I didn't put a ring around that one. It could also be separated this way. You could distill by separating, because they've got different sizes. To separate. They have different sizes. Some can hydrogen bond, some can't. Some have got NHs, others haven't. They'll have different boiling points. So you can heat them up and they'll boil at their boiling points and be collected separately. That one is ionic, even though it looks organic. So it looks like it should be non-metallic. Because it's all non-metals, it looks like it might be covalent. And while it has obviously got covalent bonds in it, overall it's ionic because you've got opposite charged ions. Being ionic, we'd expect it to have a high melting point and boiling point. So if I were to heat this reaction mixture, imagine it contains some leftover haloalkane plus all those products, I'd expect the 4 simple molecular ones, covalent, to boil first. And within that, you know what, we need to stop, but we could even go further. These 2 can hydrogen bond. So they'd have the higher boiling points. We won't worry about which one would have the highest boiling point. Probably that one, because it's a bit bigger, because it's got the methyl group on it instead of a H. But they can hydrogen bond, they'll have the higher boiling points. They can't, the tertiary amine and the haloalkane, and I'd expect the tertiary amine to have a higher boiling point than that, because, well, I assume they've both got dipole-dipole attractions, but that's bigger for sure. So probably that's got the lowest boiling point, that's the next. Then you've got the hydrogen bonders, and take a lucky dip basically and decide which is the highest boiling point. Don't worry too much about that. And then left over in the bottom of the vessel would be this ionic substance. And if there was a solvent, it would be dissolved in it. Otherwise, it would be crystals of it. But there you go. So we could separate them, but questions about that might ask you also to think about what you know about bonding, intermolecular forces, and types of bonding. Okay? Right, well done for bearing with that. I trust that that's taken you the best part of the hour, because the video is about half an hour and you've been pausing it to do your mechanisms. So that's all there is to say today. There are no further questions for you to do. Make sure you're clear on this, because we're moving on from nucleophilic substitution now. We have got a tiny little bit left to say, but it's more about the rate of reaction of those reactions rather than new mechanisms. And then we go on to something other than nucleophilic subs. Thanks for that.